A transparent crystal sat between two mechanical clamps. In its normal state, it had no overall handedness. Its atomic structure contained left-handed and right-handed patterns that perfectly balanced each other. Then researchers squeezed it. The balance broke. The crystal began interacting with light as though it had become right-handed. When the direction of the mechanical strain was reversed, its handedness flipped. Nothing was added to the material. No electric field was required. The researchers changed a fundamental geometric property of the crystal simply by stretching or compressing it. Scientists have named this newly demonstrated phenomenon the piezochiral effect. It joins a family of effects in which mechanical force changes a material's internal properties. Piezoelectric materials produce electrical polarization when squeezed. Piezomagnetic materials alter their magnetism. Piezochiral materials acquire controllable handedness. The discovery raises an unusual possibility. Future devices may be able to switch how they interact with light, electrons, biological molecules, or chemical reactions using nothing more than carefully directed mechanical strain. To understand why that matters, begin with your hands. Your left and right hands are mirror images, but they cannot be placed perfectly on top of each other. The thumb will always point in the wrong direction. Objects with this property are called chiral. Chirality appears throughout nature. Spiral shells can twist clockwise or counterclockwise. Some crystals form left-handed and right-handed versions. DNA has a characteristic helical direction. Many biological molecules also exist in two mirror image forms known as enantiomers. Those molecular versions can behave very differently inside the body. One form of a drug may interact correctly with a biological target, while its mirror image may be less effective or produce unwanted effects. This happens because proteins and receptors are themselves chiral. A molecule can fit them like a particular hand fitting a particular glove. Controlling chirality is therefore important in chemistry, medicine, biology, and materials science. But engineers have faced a basic difficulty. There is no simple universal switch for handedness. Electric fields can reverse electrical polarization. Magnetic fields can reverse magnetization. Chirality is different because it is not an ordinary directional quantity. It describes whether a structure is distinguishable from its mirror image. Researchers can create chiral materials through chemical synthesis, crystal growth, or nanofabrication. But once a structure is made left-handed or right-handed, changing it afterward is often difficult. Some methods can alter chirality near a phase transition, while specially designed light pulses can temporarily drive certain structures into chiral states. What scientists lacked was a broad and predictable way to connect ordinary mechanical strain directly to chirality. The new study began with symmetry rather than with a particular material. The researchers examined the 32 crystallographic point groups used to classify the symmetries of crystals. They asked which apparently achiral structures could become chiral when stretched or compressed along a specific direction. This sounds contradictory. How could a material with no handedness suddenly become handed without rebuilding its entire structure? The answer lies in hidden local patterns. An achiral crystal can contain small atomic arrangements that are individually chiral. Some may be left-handed and others right-handed. Under normal conditions, symmetry forces their contributions to cancel. The whole crystal therefore appears achiral even though chiral fragments exist inside every repeating unit. Imagine a perfectly balanced scale. A left-handed structure occupies one side and a right-handed structure occupies the other. Their effects are equal, so the total is zero. Mechanical strain can disturb that balance. When the crystal is stretched in one direction, one set of atomic relationships changes slightly more than its mirror counterpart. The left and right-handed fragments no longer cancel perfectly. The material develops a measurable overall handedness. Compression can reverse which local structure dominates. Changing the direction of strain can also change the sign of the effect. The researchers described this relationship using a new mathematical quantity called the piezochiral tensor. It connects the way a crystal is strained with the chirality that appears. Their symmetry analysis identified several classes of achiral crystals that should support the effect. They then selected silver gallium sulfide or Ag-Ga-S2 as an experimental test. Ag-Ga-S2 is normally classified as achiral. Its unit cell contains local atomic structures with opposite-handedness arranged so that they cancel one another. The team applied controlled uniaxial strain to the crystal and measured its optical activity. Optical activity occurs when a chiral material rotates the polarization of light. Light can be described as an electromagnetic wave oscillating in a particular direction. When linearly polarized light travels through certain chiral materials, that direction gradually rotates. The amount and direction of rotation provide a way to detect handedness without directly watching every atom move. In the unstrained crystal, the opposing local chiral structures produced no overall rotation associated with bulk chirality. Under strain, a measurable optical response appeared. Reversing the strain reversed the sign of the induced chirality. Pulling the material produced one-handedness. Pushing it produced the other. Computer calculations supported the measurements by modeling how the atomic positions changed. The strain did not need to twist the entire crystal into a visible spiral. Tiny displacements inside the unit cell were enough to upset the balance between its hidden mirror structures. This is important because the effect is controllable and continuous. The material is not limited to a permanent left-handed or right-handed state created during manufacturing. The strength of its chirality can change with the amount of strain. It can pass through an achiral state and emerge with the opposite-handedness when the mechanical condition reverses. That behavior resembles a dial more than a simple switch. A device could theoretically begin with no optical rotation, gradually become right-handed as it is stretched, return to neutral, and then become left-handed under compression. One possible application is tunable photonics. Light carries information through its intensity, wavelength, phase, and polarization. Devices that dynamically control polarization are used in sensing, communications, and imaging. A piezochiral component might alter its optical behavior through microscopic mechanical actuators. Instead of replacing a filter or rotating a physical optical element, a device could strain a crystal and change how it treats left or right circularly polarized light. The effect may also matter for spintronics, a field that uses the quantum spin of electrons in addition to their electrical charge. Chiral structures can influence how electron spins move through materials. If strain can reverse the material's handedness, it may offer another way to control spin-dependent transport. But these applications remain possibilities rather than finished technologies. The experiment demonstrated the physical effect in AG-GA-S2. It did not produce a commercial optical processor, quantum computer, or spintronic memory. Researchers must still identify materials with stronger responses, better durability, and properties suitable for manufacturing. Chemistry may offer an even more ambitious use. Many industrial reactions need to produce one molecular enantiomer while avoiding its mirror image. This is called asymmetric synthesis. Chemists commonly use chiral catalysts whose surfaces or molecular structures favor one product. A piezochiral material could potentially act as an adjustable chiral environment. Strain in one direction might favor a left-handed product, while reversed strain could favor its right-handed counterpart. That would be unusual because the same physical platform could theoretically change its preference without being chemically replaced. The study does not yet show strain-controlled production of pharmaceuticals or other enantiomer compounds. The researchers presented asymmetric catalysis as a future direction that will require separate experiments. Biological sensing is another possibility. Chiral molecules often interact differently with left and right-handed surfaces. A mechanically adjustable material might be tuned to detect or separate particular biomolecules. Again, the central advantage would be control. Current chiral surfaces are often fixed after fabrication. Piezochirality introduces the possibility of changing the surface's effective handedness while it is being used. The discovery may also help physicists investigate chiral quantum phases. In some quantum materials, handedness is connected to unusual electronic, magnetic, or optical behavior. Mechanical strain is already a powerful experimental tool because it changes distances and angles between atoms without altering the chemical composition. The piezochiral framework tells researchers exactly which symmetries allow strain to couple directly to chirality. Instead of testing materials randomly, they can search crystal databases for candidates belonging to the predicted groups. This may turn a single demonstration into a broader class of materials. However, there are practical limitations. A crystal can crack if strain becomes too large. Real devices experience defects, temperature changes, and repeated mechanical cycles. The induced response may also be too weak in some materials to be useful outside sensitive laboratory measurements. Researchers will need to discover how quickly chirality can be switched, how long the materials survive, and whether thin films or nanoscale structures preserve the effect. There is also an important distinction between inducing chirality and physically creating a new permanent chiral substance. When the strain is removed, the tested crystal returns toward its balanced achiral state. The external force controls the property while it is applied. That reversibility is not a weakness. It is the feature that makes the effect potentially useful. For more than a century, piezoelectricity has allowed pressure to become voltage. It appears in microphones, ultrasound devices, accelerometers, precision actuators, and small ignition systems. A simple mechanical deformation can generate or control an electrical response. Piezochirality proposes another conversion. Mechanical deformation becomes handedness. The crystal does not visibly turn into a spiral. Its shape may change by an amount too small for the eye to notice. But inside each unit cell, opposing atomic structures stop canceling. Light passing through the material detects the imbalance. The broader lesson is that an apparently neutral material can hide properties that symmetry keeps locked away. Breaking that symmetry does not necessarily require a dramatic transformation. A small force applied in the correct direction can reveal an order that was already present locally. Before the experiment, the silver gallium sulfide crystal contained both handed structures in perfect balance. It was neither left-handed nor right-handed as a whole. The researchers stretched it, and one side of that hidden geometric competition became stronger. They compressed it and the winner changed. A mechanical force had become a reversible control for chirality. What began as a subtle movement of atoms may eventually lead to materials that change their interaction with light, spins, chemical reactions, or biological molecules on command. For now, the experiment has established the first step. A crystal with no overall handedness can be squeezed into choosing one.